So for the alcohol functional group, the acidity, so how strong of an acid that alcohol is dependent on the structures that it's bonded to. Right, so I kept things fairly similar, but here's three examples. You have a cyclohexanol, a phenol, where we have a bunch of pi electrons around that carbon ring, and then fluorocyclohexane, where we have a fluorine group attached. So just those small differences can affect the acidity of the alcohol. Basically, any different structure will change how acidic the alcohol is, and there's a variety of reasons for that. The main one we're going to look here is, what's this fluorine going to do? And that's inductive electron withdrawal. So inductive electron withdrawal is essentially the pull of electrons through sigma bonds, through single bonded regions, based on higher electronegativity atoms. So having a more electronegative atom somewhere further down the structure can impact where the electrons go in the molecule, basically. So which one is the strongest acid? In this case, it's actually the alcohol with resonance stabilization. So if we form the conjugate base here, this extra negative charge has a lot of room to go. So we can draw a lot of resonance structures here that are going to stabilize that negative charge. All right, this one is the most stable, which gives us the strongest acid here. Right? Our weakest acid is the cyclohexanol, which has nothing going on there, just simple carbon structures. So remove the proton there, nowhere for those electrons to go, not really very spread out. Right? So this one is the least stable. Right? This is the weakest acid. Right? Leaving our inductive effect over here, which is sort of in the middle. Right, so inductive electron withdrawal can stabilize a negative charge. It can make a more stable conjugate base, but it's not as strong as an effect as resonance usually. So in this case, it's beaten out by the resonance. So what's going on here? There is a strong pull, so this fluorine is highly electronegative. So if we think about it in terms of polar bonds, from carbon to fluorine, the fluorine is stealing a lot of the electron density away from carbon, right? But for a larger organic molecule, just that one carbon is not the only thing that's impacted. If we're drawing a formal dipole, right, we're only looking at that carbon and fluorine, but in reality, what the inductive effect means is, all right, well, it's also pulling from this carbon and this carbon nearby. Right, so the electrons from the rest of the structure are all getting pulled towards fluorine. The electrons from this negative charge here up on oxygen are also getting pulled down. Right, so there's a flow of electrons through the sigma bonds towards fluorine, and that is the inductive electron withdrawal effect right there. The electrons being pulled from further in the molecule, which is going to stabilize and sort of spread out that negative charge. Right, we're stabilizing that oxygen with the negative charge by pulling away some of its electron density. Right, the higher the concentration of charge, right, this oxygen here has got nowhere to go. This one is stabilized by spreading all those electrons out through quite a large bit of the molecule. Right, here, some of that negative charge is siphoned away and pulled towards the fluorine. That's going to stabilize it a little bit. And that's essentially what the inductive electron withdrawal effect is here. It's going to pull electrons away from a negative charge, making it more stable. Right? That effect can be stronger. If the fluorine atoms are closer to the negative charge, that'd be a stronger effect. If there are more fluorine atoms, right, that can be a stronger effect. It's not always fluorine, it could be a chlorine atom. Chlorine is going to be a weaker effect because it's not quite as electronegative. So there's a lot of variety there, but this is sort of the basics for what we're looking at.